book is about an analytic version of the Langlands correspondence and applications to quantum integrable systems. This is actually my joint work. I will talk about my joint work with Pavel Etingov and David Kashdan. And we actually have a paper on the archive, which you can see here on this subject, which will appear soon in a memorial volume in honor of Boris Dubrovin. We also have another paper in the works, which hopefully will upload to the archive soon, hopefully by the end of the summer. Okay, so this is actually, it's an interesting subject because it touches upon many different topics in different fields of mathematics. So obviously in half an hour, it's impossible to do justice to all of these aspects, but I want to give a motivation anyway, a brief motivation to how this work came about. And so I would like to talk a little bit about the Langlands program. So Langlands program has been around for more than 50 years. It was launched by Robert Langlands in the late 60s. Well, the story is quite well known now, I think. So it was a famous letter he wrote to Andre Weil with a preamble saying that here are my, well, I'm paraphrasing some of my conjectures, and if you like them, I hope you like them, and if you don't, I hope you have a wastebasket handy. And so, well, the conjectures did not end up in the wastebasket. Let's just say that. So the idea of the Langlands conjectures initially was to link some very sophisticated questions in number theory to harmonic analysis. So more specifically, Langlands talked about Galois representations and motifs, and those have very intricate structure and usually very difficult to analyze. But he found that it was possible oftentimes to describe them in terms of much more tangible data from harmonic analysis, specifically so-called automorphic representations. And the famous example is the Shimura-Taniyama-Wei conjecture. Now, Shimura-Taniyama-Wei conjecture was formulated earlier in the 50s. However, it is instructive to see it as a special case of the Langlands program. So ultimately, it was understood that Langlands program could be viewed as a vast generalization of that conjecture, and as well as other statements, for instance, abelian class field theory and so on. Of course, Shimura-Taniyama-Wei conjecture became famous lately because it implies Fermat's last theorem. And so once it was proved by Andrew Wiles and Richard Taylor, first for the semi-stable case and then others for general elliptic curves, this led to the proof of Fermat's last theorem. But from the point of view of the Langlands program, the Shimura-Taniyama-Wei conjecture is really about linking Galois representations and automorphic representations. In this case, we have two-dimensional Galois representations, and they are associated to an elliptic, such a representation is associated to an elliptic curve over the rational numbers. So an elliptic curve, geometrically, we think of it as a torus. So it has the first cohomology group, which is two-dimensional. And there is an analog of this topological cohomology group called the Tal cohomology, which affords a representation of the Galois group if the elliptic of the rational numbers, if the curve is defined over the rational numbers. So elliptic curves give a nice source for two-dimensional Galois representations, elliptic curves over Q. And there are various invariants associated with these representations. Shimura-Taniyama-Wei conjecture says that those invariants can be computed by assigning to this elliptic curve a certain modular form, a very classical object, modular form on the upper half plane, essentially taking Fourier expansion and taking the coefficients. So in this case, Galois representations appear from elliptic curves. Modular forms are specific incarnations of what I call in general automorphic representations. So that's an example. And Langlands program is a vast generalization of this example. In fact, the Langlands correspondence can be formulated in three different scenarios, or you could say it can develop on three parallel tracks. This is actually best understood in the framework of André Wei's Rosetta Stone. So there's a famous letter from André Weil to his sister, which he wrote in 1940 while being in jail for refusing to serve in the military. And he wrote this beautiful letter outlining his ideas to his sister, a famous philosopher, a mystic. So he tried to explain it in kind of pedestrian terms. And the idea is that there are three tracks, there are three parallel tracks in mathematics. The first one has to do with number fields. The second with curves over finite fields. FQ is a finite field with Q elements, with Q being power of a prime. And the third one is curves over complex numbers. We can also think of them as Riemann surfaces. So here, the number field is a finite extension of the field of rational numbers. So for instance, just the field of rational numbers is a good example. What about a curve over a finite field? So if you have a curve over a finite field, we can take its field of rational functions, call it function field. And in many ways, it's actually similar to the field of rational numbers or general number field. So for instance, if you analyze ideals, etc., in the ring of integers of this field, you will see a very similar structure. It's a Dedekind domain and so on. So it's been understood for a long time, certainly in the 19th century, that function field for a curve over FQ behaves very similarly to a number field, even though a function field is a field of positive characteristic, while a number field is a field of characteristic 0. So for instance, if you just take the projective line over finite field, simplest curve, simplest projective curve, then what is the field of rational functions on it? It just explicitly, we can think of such a function as a ratio, as a fraction, p divided by q, where p and q are relatively prime polynomials. So it surely looks very similar to rational numbers, which are ratios of relatively prime integers. Okay, so that explains the similarity between these two tracks, or these two scenarios. And then, of course, curves over finite field, curves over complex field. Very different, yes, but from the algebraic point of view, there are a lot of similarities as well. And so that's how these last two tracks are parallel to each other. Okay, so the original Langlands program was formulated in these two domains, in these two scenarios, number fields and function fields for curves over finite field. I mentioned an example of the Langlands program which unfolds in this column, over this track, because it has to do with the field of rational numbers. But there are similar statements and conjectures and theorems in this case. Okay, so now, what happens? What exactly is a statement of Langlands, of the Langlands program, or the Langlands conjectures? So let's take the middle column. So you have a field of functions on a curve over a finite field. And we will look at the special case, which is called the unramified Langlands correspondence. It doesn't matter at this point. So it's kind of a simple slice of the Langlands correspondence. So on the one side, as I said, you're going to have representations of the Galois group. But what is a representation? An n-dimensional representation is a homomorphism from the Galois group of f. F, again, is a function field to GLN. These are the objects on one side. And on the other side, you have harmonic analysis, as I said. But specifically here, you're going to have what's called Hec Eigen Functions. So functions which are eigenfunctions of certain operators acting on the space of functions on this double quotient. So you see, so here, I don't want to get into too much detail here. Why am I not? Yes. You have the ring of Adels, which contains the field, and you have its subring of integer Adels. Anyway, you have this GLN of this A has two subgroups, and you take double quotient. If you don't know what this is, it doesn't really matter. So it's some space like upper half, kind of similar to the upper half plane, where you want to do harmonic analysis. And the point is that eigenfunctions of certain operators on this space are in one-to-one correspondence with representations, n-dimensional representations of the Galois group. I am simplifying a little bit. So there's a couple of technical things which one needs to add to this. But other than that, this actually is not only conjecture, but a theorem proved first by Vladimir Drinfeld in the case of GL2, and then subsequently by Laurent Laforgue for general GLN. Okay, now one more ingredient of this story is the so-called Langlands dual group. You see on the left, if we think of representations as homomorphisms with values in GLN, then we may wonder whether we can actually allow other reductive groups. But let's start from the right-hand side. So instead of taking the double quotients of GLN, let's take a double quotient of some reductive algebraic group G. Okay, so what would Hec Eigen functions on that space correspond to? And it turns out that you will have, again, homomorphisms of the Galois group, but now with values in another group altogether. Well, if G is GLN, this LG, Langlands dual group, is also GLN, just happens to be the same. So it's kind of misleading a little bit here. But for instance, if you take SLN, this one will be PSLN or PGLN, the quotient by the center. So it's not that different. But for instance, if you take odd orthogonal group, its dual will be the symplectic group, and so on. So this is kind of a most mysterious, I would say, aspect of the Langlands program. It shows that there's something going on which is not quite clear. I don't know what's going on here with my file. Also mysterious things going on, but not as mysterious as the Langlands program. Okay, so that's more or less the idea. Okay. So now the key point which enables, remember we have three tracks actually. We have number fields, curves over finite field, curves over C. So far I only spoke about the first two. The key point of transferring all of this to the complex domain, the case of curves over C, Riemann surfaces, is this realization that this double quotient actually has a geometric meaning. This is a set of equivalence classes of G bundles on X, principal G bundles on X. Remember, G is a reductive algebraic group. So now we could actually, this statement is true both when X is over a finite field and when X is over a complex field. When X is over a finite field, we consider space of L2 functions on this set. It is endowed with a canonical measure called the Tomography Measure, which is basically comes from Haar measure on various local factors of this double quotient. And then you have the algebra of commuting Hecke operators on it. But suppose that X is now over C. So then we are talking about the set of points, or what's called the moduli stack of G bundles on X. Now, yes, it's possible to define the space of L2 functions on it, and I will talk about it in a moment, but they're not going to be algebraic, obviously. You see, so for instance, if you just take simplest one will be just the Picard variety of an elliptic curve, which is isomorphic to the elliptic curve itself. So if you just take an elliptic curve, it's a compact manifold. So of course you can take a space of L2 functions with respect to some measure, or in fact, the better thing to do would be to take, in this case, actually the canonical bundle is trivial. So there is actually canonical product. So canonical inner product. So you can define the L2 space, but obviously these are not going to be holomorphic functions. They're only constant holomorphic functions. So that's the quandary which has kind of perplexed the pioneers of this field when they tried to transport these ideas to the case of the complex numbers, because they wanted to do it in an algebraic fashion. You see, theory for curves over a finite field in many ways was amenable to algebraic geometry, and they wanted to use the same methods over C. And that showed that, well, it somehow is in contradiction with the idea of taking L2 functions, because they are not holomorphic, not algebraic. So instead, the pioneers of this field, Drinfeld and Lamont, proposed a different theory. They proposed that we should consider not functions, but sheaves. And that theory, then the theory will be algebraic holomorphic. What this means is instead of functions on band G, we consider the derived category of sheaves. What kind of sheaves? Well, specifically D modules on band G, modules over the sheaf of differential operators. Instead of Hecke operators, linear operators acting on functions, you will now have functors. So now, of course, this day, so this is 1980s. So these guys were way ahead of their time, because these days, of course, it's sort of, it's almost a reflex to categorify things. It's almost a reflex to go and say, oh, you have a vector space. Let's try to construct a theory where this vector space is replaced by an abelian category or derived category and so on. But these guys did it already in the 1980s. Of course, I should say, this all goes back to the ideas of the great Alexander Grothendieck, because he was really the one who realized that, for instance, even for curves over finite field, in the theory of curves over finite field, a lot of things could be done in terms of sheaves rather than functions. So that he was really the source of this idea. Anyway, this way we get this geometric Langlands correspondence, which is really unfolds in the category of sheaves on band G rather than functions. Now, Robert Langlands, the father of the Langlands program, was not satisfied with this. And he has been asking for years whether it's possible to construct an analytic theory. He was like, okay, you guys like the sheaves and so on. But, you know, I'm old school, kind of, I'm paraphrasing. I'm old school. I like functions. So I like analytic theory. Is it possible to construct an analytic theory for curves over complex numbers, where you have an honest to goodness spectral theory on the space of functions on band G and not on the category of sheaves? And so Langlands actually wrote a paper 2 years ago, which is on the website of the Institute for Advanced Study, in which he asked this question more specifically, and he proposed some strategies of how to build such a theory. So now in the joint work, in my joint work with Pavel Ettingov and David Kashdan, we have shown that it is indeed possible to construct such a theory. So in this theory, it kind of develops in parallel to the geometric theory of Drinfeld, Lamont, and others. I should also mention Alexander Belenson, whose joint work with Drinfeld has advanced this field tremendously in the last 20 years, or perhaps more, 30 years. So, but the two theories coexist, and in some sense, they are complementary to each other, and they actually feed off each other. So unfortunately, I probably won't have much time to explain that interface between them, but they are not in contradiction. They are, in retrospect, it's kind of clear that both have to exist, okay? But anyway, in this theory, however, in this theory, instead of considering Hecke operators, which are prevalent, which are present in the theory of curves over finite fields, in this theory, we actually consider differential operators on band G. But both holomorphic and anti-holomorphic, and this is a kind of a new element, something that hadn't been considered before. Although I should mention an earlier work also by Jörg Teschner, who also considered this picture in some cases. And it kind of makes sense, because you see Hecke operators come for specialists in representation theory over local fields. Hecke operators come from the so-called Hecke algebra, and specifically spherical Hecke algebra, which we consider in the case when you have, say, a reductive group over a local non-Archimedean field, such as a p-adic field or formal power series over a finite field. But when we go to Archimedean fields, so say GLN over complex numbers over real numbers and so on, we don't consider usually Hecke operators. We consider the center of the enveloping algebra, and the center is corresponds to the differential operators. Okay, so in some sense it's meaningful to do that, even though in the new paper in preparation with Kashdan and Ettingov, we also construct analogs of the Hecke operators. So it's possible to construct analogs of Hecke operators as well. They're integral operators. But today I will just talk about the differential operators. So here there is some construction. So I will kind of go quickly over it, because in a sense it's not so much relevant at this sort of level of resolution. We considered L2 space. In a more general situation, in other words, Hilbert space of L2 half densities actually, in a more general situation where it's not just band G, it's not just G bundles on a curve, but you also have finitely many points, a set of points, which I call S, and you consider moduli of pairs. So you have a G bundle, principal G bundle on X, and you also have a reduction to Borel subgroup of G in the fibers of this bundle at every point in X. Okay. So then, how to define the Hilbert space? Well, we don't want to define it on the stack, so we need a manifold, and we just take two functions on it, or sections, and so. But in some special situation, we have, namely, if the genus of X is greater than 1, or if X is an elliptic curve, but there is at least 1 point, or the curve is projective line, and there are at least 3 points. But actually, effectively, it means at least 4, because if there are only 3 points, the moduli space is just 1 point, so its theory is kind of vacuous. In this case, there is an open dense subspace, actually, of stable pairs, for which the group of automorphisms is the center. And so then we simply take, we define the bundle of half densities on it. And we take the space of smooth, completely supported sections of this line bundle. It's kind of a natural thing. How would you define a Hilbert space? You just take smooth, complex supported. If you have a non-compact manifold, you will take smooth, complex supported sections, and then you will take a standard inner product on it, and you define its Hilbert space completion. That's your Hilbert space. When I say L2 functions, it's not really functions, because if you have 2 functions, you take the product, you get a function, and then you need a measure of integration. But if they are sections of the bundle of half forms, square root of the bundle of volume line bundle of volume forms, then you don't need a measure. You can just take the inner product and then you just integrate, because you get a volume form automatically. Okay. So let me drop the subscripts G and S for now. Let's realize that this bundle of half forms is actually tensor product of the holomorphic part and anti-holomorphic part. Obviously, holomorphic part is a square root of the canonical line bundle, and the other one is the square root of the anti-holomorphic canonical line bundle. Both exist, as Bellinson and Drinfeld have shown. Moreover, Bellinson and Drinfeld have shown, and in that they used actually representation theory of affine Kac-Moody algebras. Well, since this is an algebra conference, I would like to kind of make a small remark about this. The differential operators, say, on a group G come from the center of G. So here we are kind of doing something similar, but for the loop group, because we are considering this moduli space of G bundles, which is kind of like a homogeneous space for the group G, but in the infinite dimensional context. So the key role here is played by the loop group of G, or more precisely, affine Kac-Moody group or affine Kac-Moody algebra. And so the question then is to describe the center of this enveloping algebra of this affine Kac-Moody algebra. And it turns out that exactly at a special level called this critical level, there is a large center. And lo and behold, this critical level precisely corresponds to taking the square root of the canonical line bundle. So everything is consistent. You get differential operators to exist on precisely the line bundle you want, because on the line bundle for which you would be able to get the Hilbert space when you combine it with its anti-holomorphic counterpart. So Boris Feigin and I, years ago in the 1992, actually proved that there is a large center in the enveloping algebra of an affine Kac-Moody algebra at the critical level. Okay, and we even identified with an algebra for so-called functions on space of opers for the dual group. So Bellinson and Drinfeld have used this result to infer there is a large commutative algebra of global holomorphic differential operators on the sections K1/2. So you see, they were interested in the holomorphic part because they were building an algebra geometric theory. They were building the geometric Langlands correspondence. So they did not care about anti-holomorphic line bundle, this one, or differential operators acting on it, you see. They were able to describe this algebra, but obviously this algebra acts on this tensor product. It acts on this factor. And in addition to that, we can take complex conjugates of these differential operators. Now, if you have holomorphic differential operator and anti-holomorphic differential operators, they obviously commute with each other. Holomorphic commute among themselves, anti-holomorphic commute among themselves. You get a large commutative algebra of differential operators both holomorphic and anti-holomorphic, which act on the sections, on smooth sections of this line bundle of half densities, which is what we want. We want the commutative algebra to act there, because then we can do spectral theory of these operators. And that's what Ettinghoff, Kashdan, and I did. We considered the spectral problem for this algebra. So then we are in the deep waters of functional analysis, which I know Kyiv has, reputation in this field. So I'm kind of proud to talk about this at this conference, even though this conference is an algebra conference, but algebra is never too far from functional analysis. So you have antilinear involution, and you have kind of operators which give symmetric operators, sort of real part give you symmetric operators, and you want to promote the symmetric operators to self-adjoint, which is a non-trivial problem, as anyone who studied functional analysis would tell you. And so with Ettinghoff and Kashdan, we were able to define an essentially self-adjoint extension of this operator. So this is the main technical issue. So the conjecture we came up with is the following, that this part of symmetric operators, this AR, the real part, can be promoted to essentially self-adjoint operators. And moreover, the joint spectrum of these operators is in bijection with what? Guess what? It's exactly the kind of data you would expect from the Langlands program. In Langlands program, remember, we had Galois group, homomorph from Galois group to the Langlands dual group. But in geometric situation, Galois group gets replaced by the fundamental group pi1. This is a well-known analogy between the fundamental group and the Galois group. If you have a manifold and you have the field of variety and you have a field of functions on it, the Galois group of that field has a geometric analog, which is the fundamental group of that variety. Well, or more precisely, with this variety with points removed. But anyway, so we get exactly the right kind of data. A surprising element is that we get homomorphisms with values in a split real form of this Langlands dual group. And this was really a surprise, because oftentimes you expect to get unitary, compact form, unitary group, and so on. But in this case, specifically, we get the real form. So this correspondence, this bijection between the spectrum of these operators, holomorphic and anti-holomorphic, remember, differential operators acting on this Hilbert space of band G, and equivalence classes of special homomorphisms from pi1. They're not all homomorphisms, they're special homomorphisms, which are discrete in the space of all homomorphisms. The technical term is LG opers with real monodromy. I refer you to my paper with Kashdan and Ettinghoff for more details. This can be viewed as an analog of the Langlands correspondence for curves over C. It's kind of answering Langlands' question. Moreover, we prove this conjecture in the case when the group is SL2 and the curve is P1, projective line, and we have more than 3 points. Actually, in this case, a similar conjecture was proposed earlier by Jörg Teschner, as I mentioned. And this is where integrable systems come in. So the point is that, what are we doing? We are trying to find joint eigen functions or eigensections of commuting differential operators, right? So that's exactly a setup of quantum mechanics, a setup of quantum integrable system. And what is the quantum integrable model? So this is the point I wanted to make, a kind of a punchline, that in this special case, when you just look, the curve is projective line, is just P1 with finitely many points where you take barrel reductions, you get a kind of a doubling of this, what's called the Godin model. Godin model is a very important quantum integrable system, but usually it's considered just in the holomorphic part. So in fact, with Fagin and Rishtikin in '94, we were able to describe the spectrum of that model using these ideas, but only of the sort of holomorphic part. And the new element here is that we're combining holomorphic and anti-holomorphic degrees of freedom. And I hope it's clear why. So this is what I tried to explain earlier in the talk, why this is essential. It is like, going from holomorphic functions to harmonic functions. We know harmonic functions can be written as sum of holomorphic, anti-holomorphic, but a better analogy would be take exponential of a harmonic function, then it's a product of holomorphic, anti-holomorphic. Now, in general, you don't, this is a kind of abelian case, so it's a product. In general, it's not going to be a product. It's going to be sort of a sum of bilinear combination or sesquilinear combination, holomorphic, anti-holomorphic. That's more or less what our theory is in contrast to the standard geometric theory. And so in this case, more specifically, so we have this, I'll just show you a couple of formulae and I'm done. So this is like almost the last slide. So it's actually very concrete in this case. Basically, you are dealing with P1 to the power n, where n is the number of points. More precisely, it's number of points minus 1, because we also have point at infinity. And the Gaden operators, these commuting operators, they are given by very explicit formulas, where so E, F, and H are the standard elements of SL2, which acts by holomorphic vector fields here. And so each operator gives rise to a holomorphic differential operator here, you see. But in addition, we can do, by the same formulas, we can also construct anti-holomorphic, because the same Lie algebra also acts by anti-holomorphic vector fields, you see. And so the Hilbert space is just a space of L2 sections of a line bundle of half forms on this. And the algebra, you form symmetric combinations of these guys. So for instance, the sum of holomorphic and anti-holomorphic, or the difference divided by I. And it can be extended to, as a canonical extension to self-adjoint operators, essentially self-adjoint operators. And then it turns out that if you have joint eigenvalues of this HI on this Hilbert space, it's natural to form the second order Fuchsian differential operator. And it is this episode where this mu, the eigenvalues, appear as what's called accessory parameters. So that it's a Fuchsian differential operator on P1 with regular singularities at the points Zi and infinity, which means that the singularity has order 2, but also you have the subleading term, and the coefficient in the subleading term called accessory parameter will be precisely the eigenvalue of the Gaden operator. And guess what? Mu I appear as adjoint eigenvalues on the Hilbert space for these operators. Well, then because these operators become self-adjoint, then the eigenvalues of HI bar will be mu I bar. So it's really just mu i's which define the spectrum. This Fuchsian operator will have real monodromy representation. PGL2 is a Langlands dual group in this case to SL2, because our group G is SL2, and this is a Langlands dual group. And moreover, there is a bijection between the spectra of the self-adjoint operators, Gaden operators and their complex conjugates, and these Fuchsian operators with real monodromy. That's how geometric Langlands correspondence gets transformed into analytic Langlands correspondence by including both holomorphic and anti-holomorphic degrees of freedom. And after that, the expectation of the Langlands program becomes a statement about a quantum integrable system, namely holomorphic times anti-holomorphic generalization of the Gaden model, right? And we're considering the joint eigenvalues of these commuting differential operators, and lo and behold, they are parameterized by data associated to the Langlands dual group, homomorphisms from pi1 of P1 without these points to PGL2R. Well, that's all I wanted to tell you today. Thank you for your attention.